Hello, today we want to answer the question, why is the sky blue? Probably one of the most common questions that everybody has asked at some point in their life. So the quick answer is that the sky is blue because of a process called Rayleigh scattering. What that means is essentially the sunlight that's coming in is scattered off of the atmospheric gases that we have in the upper atmosphere. Our atmosphere is predominantly nitrogen into nitrogen molecule, two atoms of nitrogen together, and oxygen, O2, which is two atoms of oxygen bonded together. Now in the upper atmosphere, these gases interact with the incoming sunlight in such a way that the blue light, the blue part of the spectrum, is actually scattered, meaning it's redirected, so to speak, to our eyes more than the other colors. We'll talk about it in a minute, but this process also explains why not only is the sky blue, but it explains why our sunsets are red. So to understand in a little more detail, we have to roll up our sleeves and dive a little deeper. So what is light anyway? Light is an electric field oscillating and a magnetic field also oscillating. So you can see in this picture, you have an electric field, which is a sine wave, and a magnetic field, which is a sine wave. Now, they're oriented 90 degrees relative to each other. So the degree of propagation is 90 degrees from the electric field and the magnetic field. Now this is, I think, a better picture here because it shows the arrows. You can think of these little electric fields as little arrows, little vectors, which switch direction and they oscillate very rapidly, right? The faster the oscillation, the higher the frequency, the higher the energy of the wave, and the bluer the color of the wave. And 90 degrees to that, you have a magnetic field component oscillating as well. Now, it turns out that all light, we call it electromagnetic radiation. All light, X-rays, light, infrared, all of it is all electromagnetic radiation. It's electric fields oscillating 90 degrees to magnetic fields and propagating 90 degrees. You can see the direction of propagation on the figure here, 90 degrees to those electric and magnetic fields. All right. Now, the thing you need to realize is that a electric field, when it oscillates, it pushes electrons around. It can push any charged particles around. So that is how all light behaves. What you learn when you study Maxwell's equations is that an oscillating or a changing electric field actually causes a magnetic field to occur. But then an oscillating magnetic field also causes an electric field to occur. So the two go together, and that's why they propagate together, because a changing electric field causes a magnetic field, and a changing magnetic field also causes a changing electric field. So together they propagate through space. Now the thing you need to know is that when an electric field comes in the presence or near a charged particle like an electron surrounding a nitrogen molecule, it begins to push those electrons around. If you think of the electric field being my finger, it's going to push charged particles. It'll push electrons in one way and protons in another way. So as soon as that wave hits one of these nitrogen molecules or oxygen molecules, it begins to shake the electron cloud which is surrounding these molecules. So you can kind of think of it as what happens is the energy of the incoming wave sort of gets absorbed by the electron cloud because it's going into shaking the electron cloud. And then secondarily, anytime you have an electron that's accelerating, meaning oscillating back and forth, it re-radiates photons out or electromagnetic radiation from the electrons. In fact, that's how all antennas work. You see a long antenna on a car. The reason they're long and slender is because we have a circuit that sets up oscillations of the electrons in this long antenna, and that causes a changing electric field and a changing magnetic field, and then they can detach from the antenna and propagate as waves through space, right? And the same sort of thing is happening with the atoms in the molecules in the upper atmosphere. When a photon of light hits the nitrogen molecule, it shakes it, and when it shakes that electron cloud, the electrons re-radiate electromagnetic waves into space. But here is the kicker, right? Not all incident frequencies and wavelengths can actually shake the electron cloud as good as the other colors. It turns out that red and longer wavelengths aren't able to actually shake the electron cloud as easily, and the shorter wavelengths actually can do a much better job of shaking the electron cloud. So that's why we see the blue light scattered, because the blue light is what is able to shake the electron cloud, so to speak, to oscillate it, where the red light is not as effective at doing that, so it passes right through. So I'll go into a little more detail in just a second, but that is the big picture. The sunlight is a mixture of all different wavelengths. Different colors that you see with your eyes are just different lengths of the waves. When you look at the original figure of electromagnetic waves, you see the Greek letter lambda, and the physical length of the wave just corresponds to different colors. But different lengths of waves can actually put their energy into shaking those electron clouds from molecules in the atmosphere more or less efficiently. The longer wavelengths, the reddish wavelengths, tend to pass right through the gases, and so they don't really get scattered. But the shorter the wavelength, the higher the energy, and it's able to shake the electron cloud. It's able to put its energy into the electron cloud more efficiently of those molecules and start to shake them. They begin to then re-radiate more or less in all directions. It's not exactly in all directions, but more or less in all directions. And the color that they re-radiate is the bluish colors. So when we look up at the sky, we see blue light because the incident sun light hits those atoms and molecules up there and shakes them, and then they're re-radiating blue down to the ground. But all the red colors, they just passed right through those gases. So these are more or less the colors of the rainbow. I left a couple of them out, like I left orange out. You get the point here. Red is the longest wavelength that we typically see, and the wavelength of red light is a range, but it's about 650 nanometers. What does that mean? That means if you look at the graphic for electromagnetic waves, it is the distance in meters between two different crests or two different troughs of the wave. And it's physically in meters. So 650 nanometers means 650 billionths of a meter. So really, really, really small wavelengths. Now, yellow light has a wavelength of about 570 nanometers. So it's a shorter wavelength, right? Green, I'll just go down the list here, about 510 nanometers. So a shorter wavelength still. Blue light has a shorter wavelength still, 450 nanometers. You should start to see a pattern here. What do you think violet's going to be? It's going to be even a shorter wavelength, 380 nanometers. So you can see that the different colors of the light that you see just correspond to different wavelengths. The red colors that you see in everyday life are just simply longer distances between the peaks of the waves of those electromagnetic waves that you see, whereas the bluer and the violet colors are just waves that have a shorter physical wavelength, okay? Now here's the thing, from quantum mechanics we learn that when you go into a shorter and shorter and shorter wavelength, you have higher energy. Higher energy, right? So you have red, which is relatively low energy for each individual photon. Yellow, a little bit more energy. Green, a little bit more energy. Blue, a little bit more energy. Violet, a little bit more energy. What do you think comes after violet? Ultraviolet. We don't see ultraviolet, but ultraviolet is just a little bit of a smaller wavelength than this, which means it's even a higher energy than the violet, and that's why it can give you a sunburn. That's why ultraviolet we worry about for our skin, but we don't worry about what's on the other side of red. What do you think is on the other side of red? It's infrared, which is a little bit longer wavelength than this. The reason I'm putting this out to you here is because I want to try to explain to you why some of these wavelengths are able to oscillate the electron clouds of the upper atmosphere gases and some aren't. And in order to do that, I'm going to need a prop. All right, here I have a prop. This is not a molecule, but it's a good way to learn about why this works, okay? So everything in nature has some sort of resonant frequency. This, you can think of a child on a swing set. We also can call it a pendulum. It's free to swing, and when I pull it back one way, gravity tends to bring it back to some neutral position, but then it shoots past it, and then it goes this way and this way until it eventually slows down. If I try to put energy into this, you can think of this pendulum sort of as the electron cloud surrounding like a nitrogen molecule or something like this, right? I can push on this thing. Now, we all know from pushing children that there's a nice cadence that we push with to get the child to go on the swing, you know, very nice and efficiently. If you don't push at the right frequency or wavelength, because wavelength is related to frequency, then you don't push the child as well. So let's see what happens if I push too fast. If I push this thing, Then I'm still beating with my hand. Whoop, it went up a little bit. And I'm wasting energy. You see what's going on? I'm hitting it, but I'm still oscillating my hand. I'm still oscillating my hand. It's kind of hard to do. But I'm still oscillating my hand in between the hits, right? Like this. And so every time I'm waving my hand without contacting the swing, I'm wasting energy. So I'm not putting energy in very efficiently in here. Most of the energy is lost from the incident photons. So that is one example of not being able to put energy into a system very effectively. Let's change it the other way, and let me push with a very long wavelength or a very, very low frequency and see what that does. So I push it, and then I'm still coming back, and I'm not matching it at all. I'm really slow, you see, and I'm not able to really couple energy into it very effectively because sometimes it's way over here whenever I get to the point where I would want to hit it, and I'm out of sync with it, in other words. So I'm not able to couple energy too well into it or too nicely into it when I'm pushing too fast or too slow. But if I go at exactly the right frequency, then I can put a nice percentage of my energy from my hand into oscillating this thing. Because as soon as it comes back to my hand, I'm ready to push again. This is basically called resonance. This is the same reason why, like an opera singer can break a glass. Because every thing made of matter has some sort of resonant frequency. The glass has electric forces between the molecules in there, and when you microscopically push on the glass, it wants to spring back. And if you give your voice the exact right frequency, then it can get those oscillations and the glass moving really rapidly, and you can break the glass. So why does this apply to why is the sky blue? Because we have different colors of the rainbow. We have long wavelengths, which corresponds to low frequencies. These are low frequencies. And then we have high frequencies, which are shorter wavelengths, right? And higher energy, right? So these they're not all able to put energy into the electron cloud shaking as well. The longer wavelengths are just not pushing at the right rate to get the electrons moving in those upper atmosphere electrons. But the blue and even into the violet are able to couple their energy much more effectively into those electron clouds. And that's why those colors are the ones that scatter, and the other colors, the reds and the other colors like orange, tend to sail right through. All right, that is kind of the punchline here, but let's draw the actual scattering process. It's just going to take a second. Let's say that we have the sun right here, and we have, Jason right over here on the ground right here. And I'm looking up far away from the sun into the sky, maybe right here, right? So what's going on is the sun is shooting out photons in all directions, but let's say I'm looking upward at the sky like this, to some, area of the sky like this. What am I going to see? Well, if it's blue light, so let me put the blue light here. This is like a blue photon, right? Then what's it going to look like? Well, this blue photon is able to put its energy into the electron clouds really efficiently. These electron clouds surrounding these atoms are shaking, and they're acting like little antennas, and they're re-radiating the energy. They're like absorbing the incoming energy, but then re-radiating the energy into different directions. It's not exactly the same intensity in all directions, but that's a detail we don't need to get into here. More or less, it radiates in all directions. A little bit more preferentially in some direction than others. When you study this stuff for real, you can get into the details, but it does something like this. This is called Rayleigh scattering. So when I look up at this portion of the sky, what I see is blue, because the blue light was absorbed here and then re-radiated down to my eye. So this is what I see like this. So I see blue. Now, if I look at different portions of the sky, like if I look, let's say behind me here, let me put blue down below here. If I look over here, what am I going to see? It's the same sort of thing. The blue light's going to go over here, and then, it's going to be some kind of pattern like this. Right? And so I'm going to see blue light. Now, when you look at different portions of the sky, you may see it more or less intensely blue. That has to do with the thickness of the atmosphere and the dust that's in the air, and there's all kinds of other things. But more or less, you see various shades of blue when you look in the sky away from the sun. What happens when you look at the sun? And not at the sun when you're high in the sky, but at the sun whenever the sun is very low on the horizon. Let's look at that. Let's look at that situation right here. Before we do that, in this situation here, when I'm looking up at the sky, what does a red wavelength do? Red is going in this direction. It's also hitting the atom, but it's not really interacting much with it, so the red photons just kind of go right through. So the red, the orange, the yellow, they mostly just go through, and that's why we look up here, we don't see red, because blue is the one that's re-radiated down to the ground, right? Now, let's do the same thing at sunset. At sunset, there's a sun over here, and there's Jason over here, something like this, and there is a thick atmosphere kind of in the way. I guess I'll draw it kind of like this. So this is Earth. And this is sort of the boundary of the atmosphere. It's not exactly right because I got the sun a little bit too high. Maybe I'll draw this a little bit higher, something like that. But when I'm looking at sunset, I am looking through a thicker part of the atmosphere. When I'm looking down low, I'm looking at like an onion. I'm looking through a lot of air, right? But that sunlight is still passing through this very thick portion of air, and every point along the way, the blue light is able to be scattered away, but the red light isn't really scattering because it's not able to shake the electron clouds. So what's the red light going to do? The red light's going to come right through, and that's what I'm going to see, right? But what's a blue photon going to do? Blue photon's going to hit this molecule of nitrogen or whatever in the atmosphere, and then it's going to be absorbed and then re-radiated in different directions. So you might say, well, I'll see some blue light here, but here's the thing, there's another molecule right next door to it. So the photon emitted here is going to be absorbed by this one, and then it's going to be re-radiated. Something like this. And you might say, well, I'll see this photon here, but there's another one next door because I'm looking through a very thick part of the atmosphere. So every time it absorbs and re-radiates, the next molecule over absorbs it and then re-radiates and so on, and you lose a little bit in that process along the way. So if you're looking through many kilometers of atmosphere, the blue photons are basically all scattered away, and they're scattered up out into space and down toward the ground, but they're not really going to your eye because they're kind of absorbed and re-radiated so much that they're sort of lost. They get scattered so much the incoming energy from the sun is kind of scattered away in all directions. So you don't see this blue here at sunset. What you see is the red and the orange because it doesn't get absorbed by the atmosphere and it goes right through. That is why the sky is blue. That is why sunsets are red. Probably one of the most common questions that everybody has at one point in their life. I hope you've enjoyed this. Please follow me on to the next one. Learn anything at mathandscience.com. Hello, welcome back. Today I'd like us to explore the question, if a tree falls in the forest and nobody is around to hear it, does it make a sound? I want to attack it from a science point of view. What is sound anyway? What does it mean to make a sound? What is a sound wave? What does that actually mean? How does a sound wave propagate? And then on the other end of it, how do we actually hear? How do the sound waves go into our brain and translate into something that we call hearing? That's what we're going to talk about today, and we'll answer the question, if a tree falls in the forest but nobody is actually around, does it actually make a sound? All right, so to get started, before we talk about the tree falling, right, we know that sound that a tree makes. We need to talk first in general, what is sound anyway? So if I take my hands and I hit them together, obviously I can hear a sound. What's happening there? Well, my hands and my body are inside of this room surrounded by air. Air is a fluid. I can also clap my hands underwater and make a sound. This water is a fluid as well. Now, when I bring my hands together, they're moving and they have what we call kinetic energy. And when they go to a rapid stop, to a rapid rest, that energy has to go somewhere. The law of conservation of energy says that we can't create or destroy energy. It just has to change form from one form to another. So when my hands come to a stop, where does the energy go? Well, if you clap your hands enough, you're going to realize that your hands are actually getting hot. Just like when you rub your hands get hot. So if you make a sound by impacting an object, then if you measure the temperature of your hands over time, you'll see that some of the energy from the motion of my hand went into raising the temperature of my hands. But some of that energy, because I'm compressing the air between my hands, right at the moment of contact, some of that energy also goes into jiggling, for lack of a better word, jiggling the air molecules between my hands. And in that process of putting my hands together with force, the energy goes into my hands and also into the air, into compressing the air and causing it to move. And in that process of causing the air to be disturbed, we say that a sound wave emanates from my hand. And the same thing is happening with a tree falling in the forest. The tree is composed of lots of organic compounds, one of which is called cellulose, and it's a very strong, long molecule, and it has a lot of tension in it. Just think about breaking a pencil, right? And when you try to break a pencil, it's going to spring back against your force, right? But you can overcome that much as the tree falls and overcome that springiness of the material. And that sound that we hear is all of the fibers literally releasing their tension, releasing their energy one at a time, and imparting that energy, some of it, into the surrounding air. I want you to consider a column of air, and they are more or less traveling in random directions. Some are going down, some are going this way. You get the idea. They're traveling in all directions. And these molecules collide with each other very, very, very often. And when they collide, they ricochet and bounce off and go the other direction. Now, how fast are these air molecules traveling in our atmosphere? It turns out they travel very, very fast at room temperature, right? Somewhere between 3 to 400 meters per second. That's how fast any one of these individual air molecules, the speed that it would travel before impacting and colliding with another adjacent molecule. That's the instantaneous speed of these things at room temperature. And in fact, the concept of temperature is directly related to how fast these molecules are moving. When you cool a gas down closer and closer and closer to very, very, very low temperatures, they begin moving slower and slower. They're still colliding, but they have less average kinetic energy when they're moving much, much more slowly. So we've all heard the concept of air pressure, right? We say we have air pressure on Earth, we have air pressure much higher on Jupiter, and so on and so forth. Air pressure is what we feel due to the collisions of the air molecules with a surface, right? So the air pressure is going to depend on how fast the molecules are traveling on average, and also how massive those molecules are. So if you have a gas with a very high density, lots of air molecules in a small space, that's traveling much, much faster, which means high temperature and in an enclosed volume, and if you have massive particles, then you're in general going to have higher pressure. And if you reverse all of those things down to low temperature, very low mass molecules, then you're going to have a much, much lower pressure. Pressure is important because that is the fundamental concept behind a sound wave. Now, I want us to explore what would happen to this air if I could put my hand here and just kind of push on the air rapidly. So as my hand comes to this portion of the air, I'm going to very slightly increase the closeness of these air molecules in this tube, much as you would see in this drawing right here. So over here, what I've done is I've moved my hand very, very rapidly, and I've very rapidly and quickly compressed the air, which means I've made the average distance between the molecules much, much closer. So as soon as I begin to compress it, it wants to spring back and fly apart again, because when I compress it, the collisions are happening more frequently. And so as I compress it here, then immediately the gas is going to want to spread out, and the net effect of that is this little pressure region moves a little bit to the right, because as it spreads out, and I've imparted it with energy this way, it's going to begin to want to spread out, and the whole high pressure area is going to move this way. It might spread out and diffuse a little bit, but it's in general going to want to move a little bit to the right hand side. Now, what if I do that over and over and over again? I do it very, very regularly. Or instead of thinking of my hand, think about your vocal cords vibrating. Anything that vibrates with a regular repetition is what we consider something that makes sound, okay? So think about a tuning fork, banging a tuning fork. You can see the vibration in the tines of the tuning fork, and that is moving the surrounding air, which is generating a regular and repeating pressure pattern in the air which travels away. Then I'm going to create these regular regions of pressure, and the regular regions of pressure are going to be moving in the direction that I've begun the vibration to happen. So then we can look at the distance in centimeters or meters between the high pressure areas, which are regular and repeating, and we can call that what we call a wavelength. So when you hear about the wavelength of sound waves, or the wavelength of any kind of wave, it's the physical distance in meters or centimeters between repeating patterns in the wave. So we're going from high pressure down to low, back to high. That's one cycle of back to high pressure. That's called the wavelength. It might be 5 centimeters, or it might be 3 centimeters, or it might be something much longer. Wavelengths are true for sound waves, they're true for light waves, they're true for water waves, they're true for any kind of wave with a repeating pattern. They all have what we call a wavelength. Now, if you graph this, and you can say that this is high pressure. You can graph this on a graph and you can say, well, that's a high pressure. This is a lower pressure. So you can label this axis pressure, right? And it goes back to high pressure and then back to low pressure and then back to high pressure again. Then you can connect them in a smooth curve and get that typical wave looking pattern that we always see. When you see a sound wave or even a light wave or a water wave represented as a wave, you see the crests and the troughs. That's where it comes from. High pressure is the top part of the wave, low pressure is the low part of the wave, and the distance to where the wave repeats itself is called the wavelength. That's the same wavelength as what we drew up here, represented in a different way. All right. Now, these waves are pretty far apart. The crest of these waves are pretty far apart, right? So we would call this maybe a low frequency. You've always heard the term frequency. When I talk very low like this, it's a low frequency. I can't talk very low, sorry about that. But if you think about bass in a song or a speaker, that's a very low frequency. The wave is very spread out. But if I talk much higher, that's what we call a high frequency, right? Now, sorry about that, a little funny, but the idea of a high frequency is when the oscillations are happening much, much more rapidly, so to speak, in time, right? So here, in a given distance, you only have like one oscillation, but in the same distance, you have many, many, many oscillations. So this is called a high frequency, right? High frequency. So low frequency sounds are important to hear, and higher frequency sounds are also important to hear. And the entire range of frequencies, from the low frequencies to the high frequencies, govern what we consider to be sound. All of it's considered to be sound. Right? The human ear is able to hear about down from 20, what we call 20 hertz, up to a maximum of what we say is about 20,000 hertz. A hertz means one of these cycles happens every second. So 1 hertz is one of these pressure oscillations are happening every second. So something like this would be about 1 hertz, right? 1, 2, 3, that's about 1 hertz, something like that. 20 hertz will be doing this 20 times a second, and 20,000 hertz will be doing it 20,000 times every second, and I can't make my hands move that fast. Now, this wave propagates at a speed. We call it the speed of sound, right? So at 20 degrees Celsius, which is sort of a standard temperature that we measure things at, the speed of sound is about 343 meters per second. But the speed of sound depends on lots of things. It depends on the density of the fluid there. It depends on the temperature very much because the temperature governs how fast the molecules are moving internally, and that obviously affects how the sound wave is going to propagate. It is also affected by the density of the substance and also how massive the atoms are, because very massive atoms are very hard to get moving and very light atoms are a little bit easier to get moving. So it depends on that as well. For comparison, sound can propagate through air at about 343 meters per second at the standard temperature, but through water, the speed of sound is roughly 1,500 meters per second, 1,500 meters per second. So something like 5 times faster through water. Water is more dense, the molecules are closer together, and all of the factors that go into the speed of sound make it so that the pressure disturbance can rapidly move much, much faster through water than it can through air. So we've talked about how sound is made in the sense of the vibrations and the pressure wave that is sent out. But I would argue that when the tree falls in the forest, vibrations are definitely made because that's physics. When the cellulose breaks, it goes into the air molecules. A pressure wave is going to be present no matter if someone is present or not. But the concept of what we hear as sound, what we hear is a beautiful bird call, or a dog barking, or an ambulance going by. Those are interpretations that our brain takes from the raw input of the vibrations and turns it into something that we can understand. So in order to go further, I'd like to talk a little bit about how we actually hear sound in our ears and in our brain. Now here's where I think it actually gets really interesting. As the pressure wave travels through the atmosphere, eventually, if a person is there, it's going to go into the person's ear. What happens there? So sound waves, these pressure disturbances, are going to go through the ear canal, and they're going to impact what we call the eardrum. Now the eardrum is not that big. It's only about 1 centimeter in diameter. But one on this side and one on this side, 1 centimeter diameter, is the beginning of the process of everything that you've ever heard in your life. From a baby crying, to a jet taking off, to a tree falling in the forest. Everything goes through this tiny 1 centimeter diameter piece of flesh right here, which we call an eardrum. So these sound waves, which are pressure disturbances, vibrate this eardrum just like you might imagine a regular drum vibrating. And that eardrum is connected to 3 bones. One of them is called the malleus, one of them is called the incus, and one is called the stapes. So these are the 3 bones, and their purpose is to take the vibrations from the eardrum and amplify them and prepare them for reception by the inner ear, which is a structure called the cochlea. Looks like a little snail here. Now the 3 loops on the top will be a different video for a different day. These loops up here govern our balance and our sense of being balanced. Helps us walk, helps us be very coordinated. It's a different structure for balance and such. But down here at the bottom, the snail-looking part, this is where the actual pressure gets transmitted into the brain. So the pressure wave vibrates the eardrum, goes through the bones, into this structure, and inside the cochlea is a fluid-filled cavity. And along the membrane here are these tiny microscopic little hairs that are suspended in the fluid. Now, as the fluid begins to vibrate from the sound waves transmitted through the 3 bones, then as the fluid vibrates, the tiny hairs begin to oscillate. And as they're oscillating and bending back and forth, that triggers these receptors here that go straight into the auditory nerve, into the brain. Now, what happens when it goes from the ear into the brain? So we have a brain here, and it's obviously a very complex structure, but the parts that we're going to be focused on here is the auditory cortex, one on this side and the other one on the other side of the brain. You can see that one side of the brain is connected to one ear, and the other side of the brain is connected to the other ear, to the cochlea of the other ear there. So the nerve impulses through the auditory nerve travel up and into the auditory cortex of the brain. Now, the interesting thing about this is that when they've done studies of this auditory cortex on either side, it turns out that different parts of that auditory cortex right here, different little subdivisions of it, are sensitive or are triggered by different frequencies of sound. Remember, I told you humans go from about 20 hertz up to about 20,000 hertz. Well, there's a different little substructure in here for the low frequencies, the mid frequencies, the high frequencies. And so as we have and experience different range of frequencies that we hear, different parts of the auditory cortex are stimulated. Now, what happens beyond that? We certainly do not know exactly how the brain works because we don't have every neuron mapped out. But we know a whole lot more about the brain and how it works than maybe 100 years ago. In general, the brain is a massively parallel computing structure. So the computers that we build today are very fast mathematically, but in general, they only do one thing at a time, or if they're doing things in parallel, just a couple of things in parallel at a time. But they do them very, very fast. Whereas our organic brains are massively parallel in nature. The sounds that are coming in are being processed by these auditory cortices on either side of the brain. But in parallel with that, the data that I'm getting from my eyes goes to a different visual cortex, which is being processed in parallel with the audio. Any thinking I'm doing about trying to decide what words I'm going to say is in another cortex that is processing higher level thinking and speech and sending impulses out to control my hands and my mouth. And all of this is happening in parallel because there's no central clock like there is in a computer that's just clocking through the calculations one after another. It appears that our brain is massively parallel doing these things all at the same time. Obviously, we don't know every little detail, but we know that when young babies are born, they don't have any exposure other than in the womb to hearing sounds. When we come into the world, for the first time, we're hearing the sounds that are in the outside environment. The vibrations are coming through the air into the young baby's ear and going into the brain. And as that baby grows up, when that baby hears maybe a bird chirping, you know, chirp, 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 bird chirping, then we will tell that baby that's a bird. And that visual cortex is a pattern of neurons firing representing the visual image of a bird, is then linked with the auditory information of the pattern of neurons that are firing for the auditory processing, and they begin to be linked together. So that when you hear a bird, you begin to associate it with the visual image of a bird. When you hear an ambulance, you begin to associate it with the visual image of an ambulance. You see, as far as we can tell, when we hear a bird, a pattern of neurons fire. What do I mean by a neuron? Those are cells in the brain that are linked together such that when one fires through an electrical impulse from one cell to another, it may have a higher or lower chance of firing to cause an adjacent neuron to fire. And then that neuron, depending on how it's grown next to other neurons, may cause other neurons to fire. So when we think of a dog, it's not one neuron that fires that's like the dog neuron. When I think of a dog, it's thousands or maybe millions of neurons that are firing, and that pattern of neurons, the pattern is what a dog is in my mind. And so when I hear a bird chirping, that sound that I can think of whenever I'm remembering what a bird or dog or goat sounds like, is a pattern of neurons that's in my supervisory areas of my brain that is trained from the auditory cortex. And when the pattern of neurons fire that trigger that memory, then I remember what that is. So everything that you've ever heard, when you think of what the sound is, you're not really directly interacting with the vibrations that happened in the air. What you're remembering that a train sounds like, what a tree sounds like when it falls, what a butterfly flapping its wings up close to your ear might sound like, what a fly going by your other ear might sound like. All of those memories, those are not direct interactions with the vibrations in the air. That is what your brain has interpreted that external stimuli to be and organized it in a pattern of neurons firing in your brain. So I would argue that we have to separate what created the vibrations in the air. That's one thing. When a tree falls in the forest, that is going to happen. Vibrations are going to happen and are going to propagate as a pressure wave throughout the atmosphere. But when it enters into our ear and goes through the eardrum into the brain, that is where, in my opinion, it begins to turn into what we consider sound. Because external to the world, it's just vibrations. There's vibrations in the air all around us. Just like there's ultraviolet that I cannot see all around me. There's infrared light all around me that I cannot see. There's gamma rays, there's X-rays. I can't see any of it, but I can, as humanity, we can build instruments to detect it. But I can't directly interact with that myself. I have no internal model of what those other things are like, other than looking at false color images from a telescope or a radio telescope or whatever. I have no idea how to experience all those things. But for sound and for light, we have evolved to be able to receive that from the environment and build a mental model. So when we say, when a tree falls in the forest, no one's there, does it make a sound? In other words, that sound, timber, that sound, I don't believe that happens. What does happen is that we have vibrations that are set up in the atmosphere. What doesn't happen is when no one is there, the interpreter is gone. So there is no sound in the sense of that sound that we associate with that tree. And that does touch a little bit on philosophy, a little bit. But I would argue that the vibrations are happening when the tree falls, but not the sound. I'd love to hear what you think about this. I'd love for you to drop me a line and tell me what you think. I hope that along this journey, I've made the discussion interesting, and I'll see you in the next one. Learn anything at mathandscience.com.